We've had Science in Club 2 years running, and hopefully it'll continue on as a regular gig in Armidale for monthly science fixes. I'm Dr. Kirsty Abbott. I've been hosting for a little while, and I'm actually really pleased next month to introduce a new host for Science in the Club, and I'm not going to give away any clues, but he's here tonight. James O'Hanlon in the front row. James O'Hanlon, who just put his hand up, runs a science podcast called In Situ Science. He's joined us just recently from Sydney as a postdoctoral fellow here, and he's going to be taking over some hosting of Science in the Club in the future. So it's nice to have some more faces hosting and asking questions. So tonight, quantum what? Thanks for coming, because it's a semi-intimidating topic, and it's kind of divided people who've said they wanted to come or not come into I'm not coming because it's too hard and I can't understand a word you're going to say, to I don't know anything about quantum theory, but I'm coming to learn something, and that's great, so thank you. I will confess that the only thing I really know about quantum theory is, well, now I know a few more things actually, but before I met Peter and Steve and talked about quantum theory, is that the word quantum is derived from the Latin how much or how great. It's a measure. It's a how big. It's quantifying things. So really, quantum theory is about the smallest unit of life. It's about the smallest thing in our universe. And so if you can grasp, and if your brain can get around the idea of very simple and beautifully simplistic terms of very tiny particles and waves at the same time, then I think you'll be able to grasp some of the things tonight. So welcome. Thank you for grappling with quantum what tonight. So our speakers, I'll introduce them. First, we have Dr. Stephen Bosi. He's a senior lecturer at UNE, and he came from a quantum superconductivity background and has branched into a whole heap of physics research. And he's going to start off our night tonight with a talk. And we also have Dr. Peter Rodhe next to Stephen. We're lucky to have Peter up from Sydney. In fact, yesterday he was in India, and he has a long association with Armidale and with science in Armidale. And I know we've got multiple science families actually here, and it's nice to see that. And Peter's going to tell us a little bit more about his research into quantum mechanics and theory, and I don't even know what to call it. That's why I had to call this night Quantum What, because is it theory, is it quantum mechanics, is it quantum... what is it? So, without further ado, to kick off the night, please welcome Dr. Stephen Bosi. I'll move that.
I'm in a quantum entangled state here.
Thanks to me.
Thank you for setting that one up. Okay, now... I'm only really a quantum of a quantum physicist. My illustrious colleague over here is much more of a quantum physicist than I am, but I've kind of touched on a little bit of quantum, so a little bit of my background so you know what I mean. I did my PhD in superconductivity, and superconductors are those things that have perfect conductivity, zero resistance, but they also do things like you can float magnets on them and stuff like that. And the explanation for how they work is utterly quantum. So that's my first touching on quantum. Oh no, that was my second go at it. I spent a bit more than a decade working on sustainable energy. I also worked on some plasma physics, particularly this device here, which is a deuterium plasma that produces neutrons. And currently most of my research involved medical physics. So that means using radiation to detect and or treat cancer and other related conditions. Okay. So how I want to prove to you that I'm a little bit qualified to talk about quantum mechanics, maybe less so than my illustrious colleague here. But my first dalliance with quantum mechanics, apart from, of course, undergraduate physics where teach you a little bit of quantum theory, was I did my honours project was doing quantum chemistry, calculating quantum properties of small organic molecules. There's a little picture out of my thesis there. So, a little bit of quantum mechanics there. And then after my PhD, where I was working on superconductivity, which was mostly really about the crystallography of the superconductor crystals, but it got me interested in the quantum aspects of it. So I did a little, spent a couple of years unsuccessfully trying to detect the Aharonov-Kasher effect in superconductors. There's the gear I used. For those of you who know a little bit more, that is vaguely related to the Josephson effect. Now, I just want to warn you, never meet your heroes. Okay? Josephson effect was discovered by a fellow called Brian Josephson, and he got his Nobel Prize for something that was just distracting him from his PhD. We all try to get our postgrad students to say, look, stop getting distracted and just keep writing a thesis. Well, he got distracted and won a Nobel Prize. So I figured, maybe if it worked for him, maybe I'll allow myself to be distracted and maybe I'll get a Nobel Prize. It hasn't worked yet, but anyway, I did meet him many years later and turned out to be a complete crackpot. He just got totally into the whole spirituality of quantum theory thing, and yeah, anyway. All right, so classical physics is all that stuff that started with Galileo and Newton, okay? And the quantum mechanics is all the stuff, that we're going to talk about tonight. So I'm going to try to see if I can explain the difference between the two. So in classical physics, the meat and potatoes of classical physics is a thing called a trajectory. Okay, trajectory is you kick a football in the air and it goes through the air in this curve, right? So a trajectory is a continuous line that specifies a particle. A particle could be a football or it could be an electron, but so it specifies its speed, its position, and times, and it's continuous. For every single possible division of time, there's a definite position, a definite speed, a definite energy, a definite whatever. Okay. And generally speaking, these are the solutions to Newton's laws plus any other laws that, followed that, like Maxwell's equations and so on. However, quantum theory is different. And one of the consequences of how nicely Newton's laws all fitted together was another physicist called Laplace came up with this concept we now call Laplacian determinism, and he said that in principle it may be possible that an intelligence sufficiently supreme would be able to know all the initial positions and states of all the particles in the universe, and if you know all the laws, then you can predict the future with complete certainty. Now, he didn't mean that you could practically do that, but he thought that in principle you could. It might be possible in principle to predict the future with complete certainty, and that means that the future is basically set down from the moment that the universe is created. Okay, and that there's no slop in that. It's sort of like a physicist's version of what do they call it? The theological position. What is that? Predestination. Yes, sort of a physicist's version of that old theological concept of predestination. That the moment that everything was created, the future was wrapped up. But quantum mechanics, it blows that up. Okay, so in case of quantum physics, you don't have a trajectory. You don't have this continuous line when things move that has a definite position and state at every given time. What the meat and potatoes of quantum mechanics is a thing called a wave function. And the wave function is not a continuous line, but it's a fuzzy cloud that specifies the probability of measuring a particle's position, its speed, its energy, blah, 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 blah. But it's probabilistic. And these are solutions to something called Schrodinger's wave equation. Okay? So you can see there that if I walk down the street and I ask random people, draw a picture of the atom, most people will draw that. Okay, that's roughly 90 years old. This is more like what a quantum mechanical atom looks like. Instead of having these nice little orbits, you've got this fuzzy cloud of probability. Okay, that tells you where the electron is likely to be, not where it actually is necessarily. And what comes out of that is what we call quantum indeterminacy. Okay, so the future is not written in stone. It's uncertain. It's indeterminate, and that's in principle indeterminate. It's not just that it's impractical to know. It's actually built into the structure of the universe that it's indeterminate. Yeah.
I'd like to contest that, because what quantum mechanics says
Yeah.
is that the observation can't be predicted.
Oh, yeah, okay.
The position could be,
Yeah.
at the moment you observe, you change the system, which in classical mechanics, the observation is independent of the system.
Yeah.
It doesn't fit us. In quantum mechanics, the observation is a change in the system. So it doesn't undermine the loss of determinism.
Yeah.
You could never test for the determinism.
Oh, sure. That on its own doesn't blow up the determinism. But it's the other stuff that does. But thank you. That was a very nice explanation. You saved me a couple of minutes. No, I'm not at all. Good. I want that helps me a lot. So let's talk a little bit more about this wave function thingy. Okay. So you're all familiar with different kinds of waves. There's water waves on water, and there's sound waves in air, and there's Mexican waves, and we're all familiar with waves, and we realise that if you play a guitar, then you've got a wave running up and down. There's a little transverse wave running up and down the string as the string vibrates, and so on. So what kind of wave is this quantum wave function? Okay. Well, in order to answer this question, the answer to this question is owed to a very good choice of grandparent by Olivia Newton-John. Okay. So she had the wisdom to choose her grandfather to be Max Born, a German Nobel Prize-winning physicist. And Max Born said that a wave function is a wave of probability. I'm simplifying it a bit, but that gives you a flavour of it. A little bit more precisely, if you take that wave function, which we usually denote by that symbol, I apologise to any real Greeks in the audience, because I'm going to say psi, even though I know it's psi, okay? So that psi is the symbol that we usually use for wave function. So if you square that, then that function there tells you what the probability is of finding a particle in any particular region of space, okay? So this wave function tells you probabilities. That's all it can tell you. Yeah, sorry. So, yeah, you take the integral of it. Yeah, I'm trying to leave out integrals.
Oh, okay.
Put your hands up if you want me to put the integrals in. Well, we have two. Well, three. I know you want the integrals.
No, I specifically don't.
No, but you want them, don't you? You dream about them, don't you?
It's important because the integral is an averaging process. Looking at
I agree.
You are averaging. You are, again, changing.
Yeah.
Not what thing observed, you're averaging.
Over space. Yeah, sure, of course.
So there's still no inconsistency there,
Yeah.
philosophically speaking. It's just a different process. You're looking at the world differently rather than the world has changed.
Well, okay. I'm not going to start getting into the minimum volume in configuration space that a particle can occupy. That the fact that it's a non-zero volume of configuration space means that it's indeterminate. Okay, that's. Okay. Anyway, so basically these wave functions are waves, crudely speaking, waves of probability. Okay. And now I actually have a little YouTube video which where I sort of explain this. Well, and we'll have a look at that after the talks, okay? And it also contains some clues to some of the trivia questions. So take notes. It's in the exam. All right, so I showed you that picture of that hula hoop atom before, and I was saying that that's not what it looks like. But in fact, if you go and solve the Schrödinger wave equation around a positively charged nucleus, for all the electrons, you solve that equation, you end up with these solutions, which we call orbitals. Okay, these are little two-dimensional slices through these little three-dimensional clouds. So they don't have these nice little hula hoop orbits. They're in these little fuzzy clouds. And as I say, where the intensity of that fuzziness is high, that's a high probability. And where it's dark, where the value of that probability, with that value of that wave function squared is small, there's a low probability of finding electrons. So that's what the electron orbits look like in inverted commas, a real atom. I've actually put a bunch of orbitals here that this is how physicists chop up all the electron density. But in fact, you can actually, if you don't break the laws of mathematics doing so, you can actually form combinations of these different states to form different orbitals. And chemists, if there are any chemists in the audience? Oh, okay, right. So you're going to see a bunch of, if you're sitting in a chemistry lecture, they'll show you a bunch of orbitals that look a little bit different from the ones that I've showed there. That's because they're using different linear combinations of these orbitals. And basically it was Linus Pauling who, he was lucky to be doing his postdoc right at the beginning of the revolution of quantum mechanics. And so he got in early and he more or less kicked off the whole of quantum chemistry. Okay, so there's a few other interesting things about Linus Pauling, but I won't tell you because then it means you just cheat in the trivia quiz, right? Okay, so we've got this fuzziness, okay? Another aspect, like the other side of the coin of these wave function, the fuzziness and so on, is something called the Heisenberg's uncertainty principle. Now, I know some of you will think that Heisenberg is the meth cook in Breaking Bad, but actually this Heisenberg came first. So let's do a little thought experiment. This is sort of like the thought experiment that Heisenberg did. He said, okay, suppose we want to measure the position, speed or whatever of some particle, say an electron. Okay, now if it's a V-dub driving down the road, you measure the position and the speed and so on. You look at it. Okay, so let's do the same with an electron. So we've got an electron here and you shine light on it and then you look at what reflects off and that tells you, where the electron is, it tells you how fast it's moving or whatever. But the problem is that Einstein said that light, which had for so long been thought of as a wave, also behaves as a particle. And those particles have momentum, just like any other moving particle. So that photon that's coming out of my light source will collide with the electron and give that electron some of its momentum. So all of a sudden this electron will now, I'll give it a kick so it'll change its position, but also change its momentum. So in a sense what I'm measuring is not necessarily the position and momentum that it had before the measurement. I'm sort of measuring what I've turned it into, what I've kicked it into. Okay, so the act of measurement forces the forces that electron to adopt that position and that velocity that ultimately I measure it to have. Okay, so the act of measurement is an active part. It's not a passive thing, as Imi said earlier. In classical mechanics, you could take, in the limit, you could imagine the measurement, if you're careful enough, in the limit would not have an effect on the system, but in quantum mechanics, you can't make that assumption. So basically, the particle now has a position and speed that you knocked it into. That's not what it was before. You've actually now forced it into a different particle speed, a different position and speed, okay? So one of the effects of this is that you can't know the momentum, and momentum depends on speed, and the position exactly simultaneously at the same time. So Laplacian determinism is... Yeah, I knew you were going to hit me with that.
That says you can't verify, falsify it, because you can't perform the experiment required to. I mean, it's a question you cannot settle by experimentation.
Sure.
Not it's wrong.
But as I say,
You can't decide.
if you want to get technical about it, then we work it... No, we'll talk about it later. We'll talk about it later in the Q&A section. No, I agree. The way I've put it, I'm grossly oversimplifying the implications. But anyway, let's just run with it, and we can argue later. Okay, so not just the consequence of this, but the consequence of the mathematics that falls out of this is that Laplacian determinism can't be right in its traditional meaning. Okay. However, Einstein was, who actually, was the first person to come up with this concept of the photon. So he helped to kick off the quantum revolution. He didn't like this idea that quantum mechanics was inherently random. He didn't like the fact that it wasn't ultimately at its depth sort of some version of Laplacian determinism. So he tried to disprove Heisenberg's uncertainty principle, and the way he did it was this. Heisenberg's uncertainty principle says that the the inherent uncertainty in, let's say speed, it's actually momentum, but the inherent uncertainty of the speed and the position, if you multiply those two uncertainties together, they can never be smaller than some tiny little constant, which is Planck's constant on 2 pi, okay? But, well, it's actually Planck's constant on 4 pi, depending on how you define the uncertainty. But anyway, whatever. But then Einstein took Heisenberg's maths, okay? So Heisenberg said you can't know the momentum and position at the same time with complete precision. And Einstein said, okay, if I do a little bit of algebraic manipulation, then I can also show that you can't know energy and time with perfect precision at the same time, okay? So that means that if you want to measure the energy of a system, there'll be and if you want to measure that with high precision, then there'll be uncertainty in the time. And vice versa, if you want to measure the time at which an event occurred very precisely, then the energy becomes uncertain. Oh, sorry. The energy becomes uncertain, okay? Do I really need a mic? Okay. Okay, so Einstein said, okay, I'll take your maths and I'll fiddle with it, and it means then that energy, the uncertainty in energy and the uncertainty in time will similarly have to obey this principle. And he said that means that for very short periods of time, you know, when you're uncertain about the time, if you're very certain about the time, then the amount of energy, the uncertainty in the amount of energy will be large. And that means that that energy can appear out of nowhere, and because E equals mc squared, if energy appears out of nowhere, that means mass will appear out of nowhere, as long as it's only for a very short period of time. So Einstein said that couldn't be right, that's a violation of the conservation of energy principle. Conservation of mass and conservation of energy principle. You know? Now, Einstein's maths was perfectly correct. The Heisenberg's uncertainty principle did imply that. It just turned out that he backed the wrong horse. Okay? So Einstein accidentally predicted virtual particles. So quantum mechanics allows these things called virtual particles, which means that particles can appear briefly out of nowhere as long as they disappear fast enough that you can't measure the violation of the conservation of energy. Right. But the universe is full of these virtual particles. Talk about more about that later. Okay.
Does anyone need a drink at this point?
Einstein.
I do. You know, I don't know about you, but whenever I drink a glass of water, I imagine these 10 to the 23 tiny little boomerang-shaped molecules going down my throat. Do you do that? Yeah, maybe it's just me. I know Erica does. Okay.
Those numbers are too big.
So, for the members of the audience who don't know what 10 to the 23 is, 6 by 10 to the 23, okay, is called Avogadro's number. It's a mole of water molecules. Okay, so another thing that falls out of this quantum mechanics is this concept of the superposition of states. Basically, I showed you how the particles can be in these little wave functions. I showed you all those little wave functions around the atom, right? But each one of those little stable wave functions is called an eigenstate. Don't worry about, what the German means. Oh, okay. All right, but each of these little eigenstates represents a definite state. So it might be an eigenstate of energy. So if the particle's in that eigenstate, it means it has a definite energy, not an uncertainty in energy, but a very, very definite energy. Or it might be a momentum eigenstate. Yep.
They are precisely the observable states.
Not just precisely observable.
No, they are to observe something that falls into eigenstate.
Yeah.
And the measurement you take is the eigenvalue across an eigenstate. So
Yeah.
eigenstates are what happens when you observe something.
Yeah.
Force it into an eigenstate.
It can be in an eigenstate without being observed. It's just that.
Used up your last interjection card. After.
No, but we're looking forward to all your questions. Okay, so, all right. However, when I was saying how in Heisenberg's uncertainty principle we talked about the uncertainty of the position or the uncertainty of the momentum or the uncertainty of the speed, that uncertainty doesn't just mean our ignorance. It doesn't just mean how sloppy our rulers are. It is actually inbuilt into the fabric of matter that a particle can be in this superposition of position eigenstates. It could be spread out over a region of space. It could be in more than one position simultaneously. Or it could be in a superposition of energy eigenstates. So it could be in more than one energy. Or a superposition of momentum eigenstates. But as Imi explained very well, the moment that you measure the particle, you force it to go into a particular eigenstate. That's what a measurement is. A measurement is defined as an interaction that forces a system into an eigenstate and that you can then get the number out. So the act of measurement forces it from being in this superposition of states into a definite state, and that'll come in very handy in the next talk, that you know that. Okay? So what I was saying to Amy is that the uncertainty isn't just about our ignorance of the system, but it means that the system is inherently smeared out in energy space or in position space or momentum space. Sorry, what? Well, no, that's only if it's a bound state that it's... Yeah, if it's a free particle, then it's smeared.
From a chemist's point of view.
Yeah, but that's because it's a bound state because of that nucleus, right? Okay, so basically the act of measuring the position knocks a particle into a definite position eigenstate. And the same goes for all the other measurable quantities. So it's not necessarily in a definite position until you measure it and force it into a position eigenstate. And so therefore this concept of a strict smooth trajectory, like the football going through the air, doesn't really make a lot of sense on an atomic scale anymore. Okay, what the electron is doing or whatever the particle is doing is kind of fuzzed out in what we call configuration space, but the space where all the momentum lives and all the positions lives and all that. Okay. So, and I know Imi's going to question me on this one, but that means that the motion of particles is probabilistic. Okay. Now, so I've just told you that measurements can knock particles from a superposition of states into an eigenstate, but the measurement doesn't have to be a real human holding a ruler. Okay, it could be just interaction with other particles, collisions or whatever. So when particles interact, one particle can force a particle from one mixed state into an eigenstate. Okay, so as soon as two particles interact, it forces the particle to make a decision, if you like, what energy it has or what position it has. Okay, and so one way of thinking about this. So whenever you get these interactions, you could have gone either way. You get your sliding doors moment, if you like. One moment a particle is in two possible energy states, it interacts with another one and gets forced into one particular energy. So all throughout this particle's interactions with the world, it's flipping the coin, and it might be an infinitely sided coin sometimes, but it's flipping the coin all the time, passing through these sliding doors moments. So, you can think of it as what's going on as being this discontinuous thing that I'm talking about, where it's in this superposition, all of a sudden, bang, now it's in a definite state, and then interacts with another particle, and then am I going to go right or left? I'm going to go right. And think of it as this discontinuous thing. Or another way of thinking of it, and the maths is the same, is what's actually happening is that there's an infinite number of possible trajectories, and each time that particle has to go through its sliding doors moment, it splits up from either going, right or left. It splits up into two possibilities. There's the history that went right and the history that went left. And this is happening all the time, so it's an extraordinarily large number of possible sliding doors moments, an uncountable infinity of possible sliding doors moments. Personally, I think that's a bunch of crap. I don't actually believe that, but the maths allegedly is the same, okay? I think it's a very unparsimonious picture of the universe. if for a countable infinity of coin tosses, I might be able to accept it, but it's not. It's an uncountable infinity of them. Okay, I'll leave it at that. Now, 3 minutes. Okay. So what happens to all those other possibilities? Well, as I say, some people call that the many worlds interpretation of quantum mechanics. Now, I just want to say one thing, just so you don't get embarrassed, when you're having an argument in a pub with somebody. Don't confuse the many worlds interpretation of quantum mechanics with another thing you may have heard of, which is the multiverse cosmological model. A lot of people talk about them as though they're the same thing. They're not. I do believe this is a realistic picture of the universe. I do not believe in the many worlds interpretation. The multiverse thing, it's not a quantum thing. The multiverse thing just simply means that our universe, the universe is visible to us that started with our Big Bang, is just one bubble on a surface of bubbles of other universes that are all separated from each other, like the bubbles forming the bottom of your beer glass there. Okay, that's the multiverse concept. Don't get them confused. And if you're in a pub and somebody confuses the two, you can just, they're different. Okay, so now we take all this weirdo quantum stuff and we take it to its absolute weirdest, okay? So we have here the world's most highly qualified bongo drummer, Richard Feynman. And what I will do is I think I'll play what is possibly his opus illustrissimus, I guess if you could call it. So can we have the music, please, Mr. Music? He's saying orange juice. Okay, so apart from being a very famous bongo drummer, Richard Feynman actually was one of the people who came up with quantum electrodynamics, and he got a Nobel Prize for it. So what quantum electrodynamics takes all the weirdness of quantum mechanics and all the weirdness of relativity and sticky tapes them together to explain how electrons behave in electromagnetic fields. And the thing about this theory is it predicts certain properties of the electron to something like 13 significant figures, like one with 13 zeros after it. So I think it's about that. And that is the most accurate theoretical prediction of any quantity in the history of physics. So there's got to be something right about quantum electrodynamics. Okay, there's a couple of little philosophical holes in it, but it's getting it right to 13 significant figures, and no other theory in the history of physics has ever done that. It's even amazing that you can do that measurement to that level of precision. It's from spectroscopy. Spectroscopy can be very precise. Okay, so how does quantum electrodynamics work? Well, I said that you get these things called virtual particles. They can appear out of nowhere as long as they disappear very quickly, okay? Consistent with Heisenberg's uncertainty principle. So one of the things that Feynman said was, when your electron is interacting with the world, the electron itself has no radius. Okay, it has a zero radius. But the thing is that electron is surrounded by a cloud of a whole bunch of virtual particles that appear and disappear quickly enough to be consistent with Heisenberg's uncertainty principle. And it's this cloud of all the particles that add terms to all of the properties of the electron. So when you go and measure the spin of an electron, if you've done chemistry, you know about the spin of an electron. But the thing is that I just said the electron has no radius. How can something with no radius spin? Well, it turns out that it falls out of the properties of all that cloud of virtual particles that surround every electron as it interacts with the world. Now, it sounds screwy, and as I say, there are a couple of philosophical holes in it, but it's good to 13 decimal places. So that's good enough for me. Okay, that's basically it. That, by the way, was the effect of all that quantum chemistry had in my honours year on me.
Please join me in thanking Stay here for 2 seconds. Thanks, Steve. I think I've actually worked out why people's names are so important in physics theories. It's because you have to know who to track down to argue with about the theory. I really think if Einstein didn't know to track down Josephson, they couldn't have the right argument, right? And that's important. It was really great to see how many theories have names attached to them, because it was that person and that person's ideas. That was great. Now, one thing I didn't mention at the beginning is that after Peter talks, we're going to have a Year 2 comprehension test. Actually, it's just a trivia. But there's questions from both Stephen and Peter's talk in it. So the knowledge is floating around somewhere as a particle in the wave at the same time. So, and if you remember anything that they've said, you'll be able to answer these trivia questions. I'm going to get people together into groups of 4, I think. So just keep in mind that. Think back to what Steve just said. Take more notice when Peter's talking as well. And then we'll have trivia questions. We've got 12 questions. Thank you. After the trivia, think of questions, because we're going to have a Q&A panel with both of them after then. So keep your questions in the back of your head now. So we'll move on to more mind-blowing quantum explanations with Peter Rodhe. Join us. Please join me in thanking Peter.
Thanks, Kirsty. So Kirsty gave me quite an uphill challenge today. She phoned me up in Singapore and said, Peter, I want you to teach an audience about quantum computing. I said, sure, who's the audience? She says, people who have never studied physics. I said, how much time have I got? She says, 10 minutes. I said, sure, no problem. What could possibly go wrong with that? So what I'm going to do is tell you about quantum computing, which is my area of research. Now, for the purposes of this talk, there's really only one quantum phenomena that we need to understand, and that's what was talked about by Steve, which is the idea of superpositions. So let me just recap what that is. In the classical world, the Newtonian world that we live around today, every object has a well-defined state. By state, I mean things like position, velocity, things are moving this way, or they're here or there. Everything is well-defined, and we can measure things with certainty. In the quantum world, on the other hand, things have superpositions, which means literally they can have multiple values at the same time. So if we're talking about an atom, for example, it can be here and here at the same time. And when I say here and here at the same time, I don't mean cut it in half and put half of it here and half of it here. I mean literally you have a single indivisible unit which is simultaneously in both places. And we have ways of experimentally confirming that this is a real phenomenon and that we're not just cutting things in half and splitting them across 2 places. So this leads to the idea of the wave function that Steve talked about. The wave function is a way of characterizing this superposition. It gives us a distribution of where a particle is, for example, or how fast it's moving. And it's been known for a long time that these wave functions and these superpositions are extremely complicated to model on classical computers, our normal computers. In fact, our biggest supercomputers fall to pieces very quickly when we try and simulate things as simple as those little atoms that Steve put on the slides before me. So it's been known for a long time that we can't efficiently simulate these kinds of things. So along comes Richard Feynman, who we just heard about, and he turned this on its head and said, well, these quantum systems are so complex that we can't simulate them. What if we build a computer itself based on these quantum mechanical principles? Could it perhaps do something that a classical computer can't do? So we're exactly inverting the problem and saying we have quantum systems, they're really complex, we can't simulate them, let's use that to build a computer. So the idea of a quantum computer then is to take this idea of superposition and encode information itself into superpositions. So you all know that in a normal computer you have bits of information, zeros and ones. In a quantum computer you have what's called a quantum bit or a qubit, and it can be 0 and 1 at the same time. So a single quantum bit can be 0 or 1 or both, but a classical bit can only be one or the other. 2 quantum bits could be 0, 0, 0, 1, 1, 0 and 1, 1, 4 combinations all at once. With 3 quantum bits there are 8 combinations, 4 there are 16. It grows up exponentially. By the time you get to 100 qubits, you're simultaneously in a superposition of more states than there are atoms in the universe. So you can immediately see that these quantum bits have extraordinary complexity, keeping in mind that it can be in all of these states at the same time, whereas a classical bit could only ever be one of them at a given time. So the idea of the quantum computer is that we prepare one of these superposition states, a big superposition of many, many different values. We pump it through this magical quantum computer, and I won't tell you how it works, but what comes out then is a superposition of all the answers. So what we put in a superposition of a whole bunch of questions we're asking, out comes a superposition of all of the different answers. And you might think, well, that sounds fantastic. I get the answer to everything at once. If I put in a superposition of all possible inputs, I get all possible answers at once. Unfortunately, that sounds too good to be true, and indeed it is. And the reason is because of the measurement problem that Steve talked about. And that is that as soon as you measure things in quantum mechanics, you disturb them. When you measure things in quantum mechanics, you never actually see a superposition. If I measure an atom, I don't see it being here and here at the same time. I see it being either here or here. So this is called a wave function collapse. When you do a measurement in quantum mechanics, you disturb the system and things collapse onto one value or another completely randomly. So going back to our quantum computer, we've got a superposition of all of the different outputs. I measure it and it collapses down onto just one output. So in fact, I only get one answer. And you think, well, that's completely and utterly pointless. That's exactly what a normal computer does. You put in one input, you get one output, you get one answer. And now I'm telling you that a quantum computer does the same thing. So what's the point? Well, the point is that waves undergo interference. As you know, in water waves, if you make two droplets somewhere else in the bathtub, they interfere. Some bits are constructive, the wave amplitude gets bigger, other areas it gets smaller. So what we do in a quantum computer is before we do the measurement, we use clever interference techniques to make all of those different answers interfere in such a way that constructive interference occurs to give us some kind of answer about the whole data set, even though it doesn't tell us what the whole data set is. So let me give you a very specific example of this. If you consider a telephone book and I say to you, find my phone number, my name's Peter Rodhe, what's my phone number? It's very straightforward to do because it's ordered by telephone number, by name. And so you look up page R, then you jump to O, you find Rodhe very, very quickly because that's how it's structured. But if I inverted the problem and said, here's my phone number, tell me what my name is, that's a very difficult thing to do. Because it's not ordered by phone number. So the best thing you can possibly do is start at page 1 and just start working your way through the phone book. And so if there are n elements in the phone book, on average you have to search through n divided by 2, half of them, before you find the answer that you're looking for. So if you've got a phone book with all of Sydney, 5 million people in it, on average you're going to be reading through 2.5 million entries in the phone book before you find what it is that you're looking for. Now there's a quantum algorithm that can do this much more quickly. It's called Grover's algorithm, and what it does is instead of making us ask n over 2 questions, we can get the answer that we're looking for with the square root of n questions to the database. So what this means is that if I have a database or a phone book with 1 trillion entries, to answer this question classically, we need to look at 500 billion different entries in the phone book on average before we find the name or number that we're looking for. But the quantum computer can do it in the square root of 1 trillion, which is 1 million. There's a big difference between 1 million and 500 billion. So this gives you an idea of the computational advantage of a quantum computer. And coming back to what I said before, the quantum computer is not giving me an answer to the whole phone book at once. It's not telling me what all the names are or all the numbers are, okay? Internally, it's in a superposition of all of those different things, but I can't measure that. Instead, what the algorithm does is carefully interferes the different terms in the superposition so that I extract a particular property, which is a joint property of all of the components in the superposition without actually telling me all of the answers at once. So there are some limitations on quantum computers. They don't give you every answer to every question at once, and this is a common misconception. People think that if you ask a superposition question, you get a superposition answer. But that's certainly not the case because of the measurement collapse problem, which we've heard about tonight. There's one algorithm in particular that I'd like to tell you about, and the reason I want to tell you about it is because it's the reason we get money to do this research, because Defence and Intelligence is interested in it. As soon as you can drum up a nationalistic agenda, you'll get research funding straight away. So this algorithm is called Shor's algorithm, and what it does is factorizes numbers. If I give you two large numbers and multiply them together, that's a pretty straightforward thing to do. You can do that on your calculator or by longhand, it's very quick. But if I give you that product, the product of the two numbers, and say, find what the factors are, what those two smaller numbers were, that's a very difficult thing to do. And to the best of our knowledge, the best algorithms we have on classical computers for doing this take an extraordinary amount of time to solve this problem. So factorizing a number that's just a few thousand digits long would take our biggest supercomputers, the age of the universe, to solve that problem. So this is an extremely complex problem. A quantum computer can do it very, very efficiently in a fraction of a second. So why is this problem of interest to intelligence? Why would they care about this abstract mathematical problem? Well, the answer is that all of our encryption today is based upon this mathematical problem. You might have heard of public key encryption. This is what you use when you communicate with people online. You have two keys called a public key and a private key. The public key can be used for encoding information or encrypting it. The private key can be used for decrypting it. So I just publicly share my public key. It doesn't matter if people intercept it, it's public. Anyone can send me messages securely, but the public key can't decrypt the message, only the private key can decrypt the message. So this is called public key cryptography. Everything on the internet is based upon this idea. Okay, so it's based on the idea of prime number factorization. Those two keys, the public key and the private key, are two numbers, and it's the product of them that you give away over the internet for everybody to see. To extract the private key from this product number, you'd have to solve this integer factorization problem. So this integer factorization problem, if you could do it efficiently on any type of computer, you would be able to directly compromise all of the internet security that we have today. This is the reason the NSA is interested, and the Russians and the Chinese are all pumping huge amounts of money into it. And all I need to do to get money from them is say, hey, you know, we're going to get spied on by China, we've got to beat them to it. So one of my colleagues had a very ingenious plan recently. He was drunk one night, going out with a few friends, and what physicists do when we go to the pub is we take the paper napkins and we write down notes and things, and you know, equations, and show each other, and this is how we have fun at the pub. So he was doing this with two very esteemed colleagues. He's very famous himself. The three of them were hideously drunk. He passes out, wakes up in bed the next morning, has no idea how he got there, but he's surrounded by all these paper napkins, and he picks up the first one, and it's something to do with number theory, this problem of integer factorization. And he looks at it and says, well, that looks pretty good. So he goes to the email and types up a letter to the NSA explaining his idea, requesting research funding for it. He's still drunk. And so the next day he gets a one-line email back from the director of the NSA saying, Dear Professor Dowling, this research proposal looks like it was written by three drunks at a bar. However, given the reputation of these three drunks, we've decided to fund this project to the full amount of money. Unfortunately, I don't quite have the charisma or the charm to be able to pull that off. All I want to point out is that if you drum up national security implications, you can get funding for pretty much anything, which is precisely what I try and do. And I recently succeeded with this, so thank you very much.
Thanks, Pete. My brain is actually sufficiently blown in the last couple of talks that I don't know about you, but I'm kind of like visualising all sorts of weird binary systems around us, and in fact, it's something that I'm going to come to in the Q&A is about tangible evidence, experimentation, and visualisation of a lot of these concepts. Has anyone got anything to say at this point? Does anyone want to raise a question? We're going to have Q&A in a minute.
I'm sure he's got a question.
I'm going to get it all the way to the last.
Okay, we'll have Q&A after.